Okay, so where we left off yesterday, I'll do a review first of what we did. It's only going to take a minute, but we learned something about certain types of graphs. And you know how we had the one graph with the marks and the attendance and the dots were all over the place? We're not going to worry about those graphs again today. We'll get back to them in a couple of days. The type of graph that we learned about yesterday is a graph that follows a straight line and goes through what we call the origin. And this is called a direct linear relation. And we came up with all kinds of examples of things that would be direct linear relations. The one we used in the example in our handout had to do with the cookie recipe and the number of grams of flour compared to the number of cookies that you could get. But this is called direct linear relation. So we need to know that this will go through the origin. The origin can be written as 0, 0. This is an x-coordinate. This is a y-coordinate. Now, I don't know what you remember. We're going to find out. Those two things, the x and the y, are called variables, right? One is called the dependent variable. One is called the independent variable. Does anybody remember which one is which? Daniel.
Is the dependent variable the y?
It is. The dependent variable is the y. So this is always the dependent variable. And this is always the independent variable. And I'm going to explain to you again how we know which is which. We'll look at a couple of examples, but this is the independent. Now, there's really no way that shows an understanding for you to decide the dependent goes on y. You can't reason it out. You probably just remembered it. Was that the case? But there is a way, if you forget, that you can reason it out. Because if you look at the first letter of dependent and you look at the first letter of independent and you put those letters in alphabetical order, A, B, C, D, E, F, G, H, I. D comes before I, right? So dependent comes before independent, and when you write things out from left to right, you're going to put them in alphabetical order. So dependent goes here and independent goes there. Okay, so that's one way you can remember. Now, you also have to know which is which by what we would call a scenario. So let's say I had a graph, and this is not going to be a perfectly straight line. It's going to be data that's a little bit all over the place, but that's okay. Would you agree that my heart rate is connected to how fast I'm running? I mean, that makes sense. Within limits, right? If I continue running faster and faster, my heart doesn't beat faster and faster. It hits a maximum kind of heart rate. But if you're talking about speed, or I'll just say exercise, and that's a variable. This is a variable. And another variable is my heart rate. One of these is the dependent variable because it depends on the other. So what makes more sense? My heart rate depends on how fast I'm running. That makes sense, doesn't it? If I turn it around and say how fast I'm running depends on my heart rate, that doesn't really make as much sense. And that means that the heart rate would go here, and how fast I'm running, well, the exercise would go here. By the way, everybody, this is not going to be direct linear relation. Because if it were a direct linear relation, it would go through the origin, wouldn't it? Does that make sense? No, because that's saying when I'm not exercising, my heart rate is 0. That would be an example like this. Right? I have a heart rate even though I'm not exercising. And I had asked everybody to try to come up with, so now that's the review. I had asked everybody to try to come up with other examples where the line would look like this. And Daniel piggybacked off of Brennan's example of the logs on the truck, and what Brennan had said originally is this. For a one that goes through the origin, you said the mass, the weight of the logs, it was logs on a logging truck, wasn't it? Yep. And the number of logs. And then I introduced this idea that it might not go through the origin. And Daniel, you gave an example that said, well, what if we said the weight of the truck and the logs, and this is the number of logs. And that would be a perfect example of one that would look like this, because when there's no logs on the truck still has a weight, so it's going to have a reading. Was anybody able to come up with another example where it wouldn't go through the origin? Nobody can come up with another one? I bet you can. What if I decided to get married? I'm not going to get married. And we were going to have a banquet. And I looked at the cost of a wedding. Well, I'll say the cost of the banquet. The banquet is the dinner dance they have. And this is the number of people I invite. Can somebody explain why this graph would start on the vertical axis? Why would that be? Yeah.
It's going to have a base cost anyway.
Right, I like that word. It's going to have a base cost. There's some cost which would be probably for the hall rental and for the table decorations and for the DJ. And all of those base costs are a full base cost. I'm going to pay whether I invite 10 people or maybe 0 people. Maybe my bride-to-be leaves me at the altar. Okay? And nobody shows up. Okay? That's maybe a bad example because I still would have had to pay for it ahead of time. But this would be what's called the base cost, absolutely. And usually these forms of relations have a base cost. Okay? And we'll start looking at that tomorrow or Monday. In the meantime, we're going to do example 2 today. Okay? So we're going to do example 2. This is my plan. We'll do example 2, and then you'll have 3 or 4 of these to practice for tomorrow. And then tomorrow we'll have an assignment dealing with this that you will get marked on. So Marquita is filling a large barrel with water from an outdoor tap. When she attaches a hose to the tap and turns it on fully, the water pressure produces water flowing at a constant rate. A constant rate. What do you suppose that means? Because sometimes in math, you know what the difficulty with math is you have all these words, and sometimes the words don't matter. You could probably answer the question without reading the words, but the words matter here. Brennan?
Is it because it doesn't go slower and faster?
So the speed that the water is coming out is the same all the time. I used to live on an acreage where I had a pump hooked up to my water source, and every now and then it would kick in to build up more pressure, and the water would come out very fast, and then it would come out slow, and it'd come out fast. There was a problem with the regulator. But if the water is always coming out at the same speed, that's a constant rate. So let's say the water is coming out at a constant speed, and I have a bucket. And I put the bucket under the hose, and it takes 3 seconds to fill the bucket. And you're behind me, and you have an identical bucket, and you put it in there. How many seconds would it take you to fill your bucket? 3 seconds. What if you had a bucket that was twice as great in size? How many seconds do you think it would take? Double the time. Well, we're getting to the idea of a linear relation here. So the barrel holds 160 liters of water, and I'm going to ask you to do me a favor and just read the numbers in your question and make sure they match up here, because I changed this in your note package this year, and I think I changed it here. I want to make sure. So it's 160 liters, and it's 20 minutes? Okay, we're good to go. So it takes 20 minutes to fill the barrel. Do you expect the relationship between volume in the barrel and the time elapsed to be linear? So if it's linear, and this is tough, this isn't easy, then if we put time here and volume of water here, and I'm putting the volume on that axis because the volume depends on the time, right? If it's 3 seconds, it'll be a certain volume. If it's 10 seconds, it'll be a different volume. The volume depends on the time. What this question is asking us is this. Will that be a linear relation? Will it be linear, do you think? So how many of you, just by a show of hands, would say yes, it's going to be linear? Okay. How many of you, it's everybody, how many of you could explain why? And it is going to be linear. Okay, so it will be linear. But explaining why is more complicated, but Daniel's going to give it a crack.
Because the water is filling at a constant rate, and it's going up at like the table's going up like every 4 minutes, and it's filling at a constant rate.
Okay, and what you're doing is you're actually kind of looking at the table and not the graph, and that's kind of the key. Is this is all in the same ball? It's all wrapped up in the same idea. So when we look at the table, and I can see you have already put in some information, let's put in some information in this table. I know we're jumping ahead to C. Don't worry about it. Okay? We know that it's 160 liters is the volume of water after 20 minutes. I hope everybody sees we're back to the same thing we did yesterday with the flour and the number of cookies. And you did it a certain way. You took 160 divided by 20 is what you would have done yesterday. And you worked out a ratio that way. I might just do the following. Oh, by the way, right? Before you turn the tap on, how much water's in the barrel? Well, nothing. What about these other ones? How are you figuring out, Daniel, did you have another one you put in there?
Yeah, I did for, it worked for me before, but I did cross multiplication.
And that's what we want to do. What you're using is called a ratio, and you're going to cross multiply. So, did you write the ratio as, and there's different ways to do it, 160 liters over 20 minutes equals X liters over 16 minutes. Is that what you did? Okay. There's other ways to do it. Okay, but that's kind of how I would do it. I like to have my unknown on the top, but it doesn't matter. Whoops, where are we? There we go. How many of you have been taught what I will call the fish thing to cross multiply? All right, so we all know how to find x, right? Now, I don't teach the fish thing because I don't generally teach the courses that lead up to this. But correct me if I'm wrong, it goes like this, right? And then you work backwards. You take this times this divided by that. Oh, that's the important thing is everybody knows, and it's called cross multiplication, everybody knows how to find x. So, calculator time. Does anybody need a calculator? There you go. And if you come in and you don't have one, always just grab one off the front counter, okay? So 128 works out to 128. Just give everybody a second to make sure you get 128. Okay, now here's the thing. We don't need to do that for everyone because these are all going up by 4 minutes. And if it's a linear relation, and it is because it's filling at a constant rate, these all have to go up by the same amount. So how much is it going up from 128 to 160? 32. So it's going up by 32 here every time the time goes up by 4. So we don't have to start at the top. We can go to the bottom and just keep taking 32 away from each number. So I take 128, and you'll do this on your calculator, and subtract 32, and I think you're going to get 96. But you can let me know if my mental math is right. And then you're going to subtract 32 again, and you're going to get 64. You're going to subtract 32 again and get 32. And as a nice check here, if you've done things right and we subtract again, you get 0. And what I have written here, everybody, that's how you know something is linearly related. That's how you know it's a linear relation. That if the left-hand side is going up by the same amount each time, then the right-hand side has to be going up by a same amount each time. So, putting this all together, it will be linear because I'm going to use the table to explain this. Every 4 minutes, the volume increases by, help me out here again, 32? 32 liters. And what I mean by that is it increases by 32 liters every 4 minutes, no matter when it is. The first 4 minutes, the second 4 minutes, from the 5-minute mark to the 9-minute mark, doesn't matter. It's going to increase by 32 liters. Let me ask you a question here. Do you have a B? Okay, so we go to C, complete the data table shown. We've done that. Which is the dependent variable? Well, it's the volume, because the volume depends on the time. Right? Which means the independent variable is the time. And then we're going to complete a graph. But I haven't put the numbers on this graph for us. We have to figure that out together. Let's label things first. And I'm going to put a title on this, and it's going to be volume compared to time. We always want to, everybody, always, in this class, write titles of graphs that way. So I'm going to go back and show something to you here. Look at the title of this graph that we did yesterday with example 1. Flour compared to cookies. It's always dependent compared to independent. So in my example that I gave us earlier, where I said heart rate, exercise, our title would be heart rate compared to exercise. You wouldn't abbreviate that. I'm just abbreviating it because I don't think we need to write it down. Does that make sense? Always y compared to x. So now we have to come up with numbers. So the bottom, well, let's put labels on here. This is time, and this is liters. So the units are liters, the units are minutes. You could put volume instead of liters, it doesn't matter to me. That, whether you call that liters or volume, that has nothing to do with you understanding the math. And I care that you understand the math. This is going to be 0 here and 0 here. So what should we do? Should we put, and don't write anything else just yet, should I put 1 minute, 2 minutes, 3 minutes, 4 minutes? Should I scale it that way? Well, no, because I want to show as much of the information that I can, and it goes up to 160 liters, doesn't it? So how long did it take for 160 liters? 20 minutes? So we want to scale this so that we end up getting up to 20 minutes. It doesn't have to be that 20 minutes is here. Maybe 20 minutes lands here, but we want to use as much of the graph as we can. So you might think, well, what if we did this? And everybody's different. Some of you it will be obvious what we do. But you might think, I'm going to say 2, 4, 6, 8. No, that's not going to do it, is it? It's not going to do it because we're not hitting 20. My next check would probably be 5, 10, 15, 20. That works. Do I have to use the whole graph? No. You don't have to use the whole graph. Some of you might go 4, 8, etc. That might be a better thing to do because those are the numbers we have. Look at your table. Look at your numbers for time. If we did that, would it fit? 4, 8, 12, 16, 20, let's try. 4, 8, 12, oh, beautiful. We still don't hit the very end, but that's okay. This will make it very easy for us to plot. What about the liters? Well, we want to go up to 160. So would this work? Looking up here. Would 10, 20, is that going to take us to it? No way. I might try 20, 40, 60, 80. Let's see. 20, 40, 60, 80, no good. What if we go 40? And 40 is going to be a nice one to use because a lot of these numbers, we'll be able to figure out where they are. We'll be able to figure out where 32 is relative to 40. Could we do this? Could we go 32, 64, 90? Why not? We can do whatever we want as long as it's the same scale everywhere. And this class is not about your graphing skills. It's about understanding the connection between the graph and what's going on. So, why not? 32, 64, 96, 128, 160. You okay with that? You know what's nice here is to graph this. It's so simple now. Here's your data. Should we connect them with a line? Well, the fact that I'm handing out rulers kind of answers that question for us. We are going to connect them with a line. And there's a reason why we're allowed to do it. And again, I'm not in a big rush in this class ever. I want to slow it down and make sure we understand things. This is the line. I'll give you a second to draw it. Now I have a question for you. A couple. Why are we allowed to connect the dots? Why are we allowed to use a straight line? Because I'm going to give you a different example right now, okay? I'm going to go with the example that I think Elijah said yesterday. And we didn't get into this yesterday, but I want to get into it now. Elijah said, and we didn't graph it, but he said the pay for a mechanic and the number of cars the mechanic works on. Remember this? We didn't graph it. We just wrote it down as an example that it said, we said the pay depends on the cars. Pay depends on cars, right? And I said, well, how do you know that's a direct linear relation? And he said, well, it's the same amount per car. So it was, I think, $200 per car. Pretty sure that's what we said. So if this was 200 and 400 and 600, and this was 1 car, 2 cars, 3 cars, you would have the following points, roughly. But they would be in a straight line. Are you with me? You with me? Why can't I draw a line through them? Why is this graph, and by the way, I could also put 0, right? Bit of a drag, didn't earn anything that day. Why is this graph not telling us what's going on? What's wrong with it? Would you agree that this point right here is 1.5 comma 300? Yeah? Will he ever get paid $300? No, he can't work on 1.5 cars. It's 1, or it's 2, or it's 0, or it's 3, or it's 4. That's really important that you understand that. Sometimes graphs, we can't connect the dots because the middle one doesn't work. It's actually the cookie one. We really shouldn't have drawn a straight line. We should have drawn a whole bunch of little dots because you can't have part of a cookie. You can't have part of a car. So now I'm going to go back to this question. Why are we allowed to connect these? Can you have this volume in the barrel? Sure. You can have any volume below that. Should we do this? Whoops. No, because when the barrel's full, it's full. The barrel can't hold more than 160 liters. So our graph in this question is simply going to end there. So we've done D, we've sketched the graph. What's the slope of the line? By a show of hands, I know there's not a lot of people here, but by a show of hands, yesterday we found slope using rise and run, and we drew a triangle. Remember that? I'm going to call that the triangle method. Or we used this, which looks complicated, but it's not really. I'm going to call that the formula method. How many of you prefer the triangle method? How many of you prefer the formula method? We're split pretty much down the middle here. So we'll do both. I'm going to pick for the triangle method, and you can use your ruler to draw this, everybody. I'm going to pick this point and this point. I'm going to pick those 2 points. And in fact, even if I do it with the formula, who wants the formula? Who likes the formula? Okay, when I do it with the formula, I'm still going to use these 2 points. Okay, but I'm going to do the triangle first. And, I'm sorry, I got to look. I want to say Aaliyah. Is it Aaliyah? Okay, I'm sorry. I just wanted to make sure. And Aaliyah, I think yesterday you had asked how we got the numbers for this triangle, and I went through the explanation. It's by subtraction, right? So this height of this triangle, what we call the rise, needs to be found by looking at this number and subtracting them. And I'm going to move this out of the way so I can write this number in here. 64, 96, 128. Is that the right number? Thank you. So we need to take 128, which is this number here, and subtract 32, which is that number, and I get, I think, 96. Can you confirm that on the calculator? 96? So the rise is 96. 96 what? Bananas, cheeseburgers, liters. That's always important. The run is this number here, this distance here, and we have to take these 2 numbers and subtract them. Right, it goes from 4 to 16. I tell you, I'm with you 3. I like the formula. I like the formula. I think it's quicker. And I'm not trying to persuade anybody else to not use the triangle. You use what works. So 16 minus 4, I believe, is 12. 12 what? 12 kittens? Which would be nice, but it isn't 12 kittens. It's minutes, isn't it? So this is minutes. So what will my slope be? Well, I'll show the work down here, and maybe I'll just stop for a second. I'm answering part of E and F, but it's all the same thing, right? We're finding the slope and we're explaining what the slope is. So my slope is the rise over the run. And we said that's equal to 96 liters divided by 12 minutes, which gives me 96 divided by 12. Oh, I want to maybe say 8. Is that what it works out to be? Okay, good. So we're getting for the slope, I'll write the word slope, equals 8. What? 8 basketballs? No. 8. Anybody want to tell me? Excellent. Liters per minute. So now, okay, we'll pause there. Are we okay with finding the slope with the triangle method? Okay. If you want to use the other method, it's really the same thing. It's just that you're not drawing a whole bunch of stuff. What you're saying is on the top, it's y minus y. In fact, I'm going to do it this way. I'm going to erase a few things here. And I'm just going to say that this point is at 4, 32. This point is at 16, 128. On the top of your calculation, you put y minus y. Y minus y on the top. 128 minus 32. And that's in liters. I just don't have enough room to write liters. And on the bottom, you put x minus x. So you're going to have on the bottom 16 minus 4. So what do we get? We get 96 liters on the top, and you get 12 minutes on the bottom. It's the same thing, right? But here's maybe one, well, there's a lot we've covered over the past couple days, but this next part is really important. If you're ever asked to explain the meaning of the slope, you just have to look at the units. If you didn't include units in there and you just got the slope is 8, it's not telling you anything. What this is telling us is the water is added at a rate of 8 liters per minute. So in my chicken wing and chicken nightmare example, my slope would have been maybe 5 nightmares per chicken wing. I have a real problem if it's 5 nightmares per chicken wing. So maybe it wouldn't be 5, maybe it would be half, but it doesn't matter. And that's the final part of this example. Okay? Any questions with that example? What you should be able to do right now is tell me what direct linear relations look like. They're a straight line that go through the origin. You should be able to make a table of values from words. You should be able to make a graph from words. I should be able to give you a graph and you should be able to find the slope. You should be able to tell me the meaning of a slope, whether I give it to you or you find it. And what we have today is about 45 minutes, and I have 5 questions from your textbook, 3 questions from your textbook that I'm saying are for homework. Tomorrow when we come in, we will go over any questions you have with this, and then you're going to have an assignment, something that you have to do, not on your own, I'll help you out, but I want you to try to do as much on your own that we will take in for marks. And then we're going to move on after that, probably not tomorrow, but on Monday. If you want extra practice, then on page 15 of your handout, there are a couple of other problems you can do if you want. You don't have to, okay? But those 3 problems are for homework. Some of the questions are going to ask you to sketch graphs. I don't want you to sketch graphs just like rough sketches. Anytime you're asked to sketch graphs and you don't have on your handout a graph grid to use, I've got graph paper up here, okay? So I'll tell you what, I'm going to put it here. This will be our place for stuff. So if you ever need a ruler or a calculator or graph paper, it's all up here. So get to work on those. I'll give you, 5-10 minutes to get settled in and try them on your own, and then I'll come around and I'll see if I can help you if you need help, okay?